In section 12.6, we're going to talk about something called the binomial theorem. So I want to start by establishing a pattern. Let's talk about what happens when you raise a binomial to a power. And we're going to use this very simple binomial, x plus y. Well, remember, anything to the 0 power is 1. And anything to the first power is just itself. And I'm going to write it like this, just because I want you to see the pattern. All right, now let's go down to squared. Okay, so what do we do to get it squared? Remember, squaring means multiplying it by itself. And then we're going to distribute. First, outside, got to get that right, inside, last. And the two middle terms are like terms. So when I add them, I get 1x squared plus 2xy's plus 1y squared. To do x plus y to the third, I'm actually going to take the previous answer, which was x squared plus 2xy plus y squared. I'm going to multiply it by another x plus y, because what's x plus y to the third? Well, it's x plus y, x plus y, x plus y. But we already multiplied two of them together. So we're just going to multiply another x plus y by the answer that we got previously. And I'm going to erase some stuff here so I have some space. In order to multiply this out, I'm going to go use the box method because it's a really nice way of doing it. So the way the box method worked was I'm going to put the binomial on one side and I'm going to put the trinomial on the other side. And then we're going to find the area of each box. So this is going to be x cubed. This is 2x squared y. This is xy squared. This is x squared y. 2xy squared. And then y to the third. So when I go and I add my like terms, which often end up on these diagonals, we're going to get x cubed plus 3x squared y plus 3xy squared plus y to the third. Now I'm going to erase this box so I can write the answer a little bit nicer. All right, so we have 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. All right, we're only going to do this one more time. We're going to find x plus y to the fourth. Well, I can do one of two things. I can either multiply another x plus y times the previous term, or x plus y to the fourth is really this multiplied by itself. So I'm actually going to use that one, x squared plus 2xy plus y squared. I'm going to do the box method. So I'm multiplying two trinomials. So I have x squared, 2xy, y squared, x squared, 2xy, y squared. And then we find the area of all the boxes. X to the fourth, 2x cubed y, x squared y squared, 2x cubed y, 4x squared y squared, 2xy to the third, x squared y squared, 2xy to the third, and then y to the fourth. And then the like terms are on these diagonals. So I'll combine my like terms, and I get x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the fourth. And then get rid of my box here. And I'm going to write my answer a little bit nicer here. So 1x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the fourth. All right, now I'm going to go back and I'm going to establish this pattern. Well, let's talk about what we see happening here every time we multiply by another x plus y. Notice that the first term and the last term are ones. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Notice that the first term from the binomial, the x, the first term has that biggest exponent, and each consecutive term seems to go down by 1. So, this is x, I have x to the fourth, x to the third, x to the second, x to the first, x to the 0. And notice that the second term in the binomial, the y's, their powers are going up. 0, 1, 2, 3, 4. And that seems to be happening in all of these expansions. But what I really want to focus on is the pattern of numbers of coefficients. The pattern of numbers of coefficients is called Pascal's triangle. In my opinion, it's one of the most beautiful things in mathematics. So, the way Pascal's triangle works, notice that it's a triangle shape. And what's happening is all the outside terms are 1s. The middle terms, if you add these two together, notice you get a 2. If you add 1 and 2, you get 3. 2 and 1 is 3. If you add 1 and 3, you get 4. 3 and 3 is 6. 3 and 1 is 4. And then the outside numbers are 1s. So the next row in Pascal's triangle will start with a 1, and then it'll be 5, 10, 10, 5, 1. And then the next row would be 1, 6, 15, 20, 15, 6, 1. So the rows have this pattern of adding numbers from the row above it. The other thing that I want you to notice with these rows is they have to do with the exponent. We call this one row 0 because if you raise anything to the 0 power, you're going to get 1. So this is row 1, and then notice row 2 has a 2 in it. Row 3 has a 3 in it. Row 4 has a 4 in it. What we're going to use this for is to do expansions like x plus y to the 8th. Nobody wants to write that out 8 times and do all the distributing. There's got to be a faster way to do it. So now, instead of distributing, we're going to use Pascal's triangle. Now, I need to know row 8. The exponent of the binomial expansion is going to tell you what row in Pascal's triangle to use. All right, well, now I got to go back because I didn't go to row 8. I went to row 6. So I need to finish and write 2 more rows. So the next row is 1, 7, 21, 35, 35, 21, 7, and 1. So that's row 7. And row 8 will be 1, 8, 28, 56, 70, 56, 28, 8, and 1. So now I'm going to use these numbers on the next page, and I'm going to forget exactly what I wrote here, so I'm probably going to have to go back and forth. So the first coefficients are 1, 8, 28, 56. 1, 8, 28, and 56. And then it was 70, 56. All right, so 70, 56, 28, 8, and 1. The other thing I want you to notice is that in row 8, there are 9 terms. In row 7, there are 8 terms. In row 6, there are 7 terms. There's always one more term than the row. All right, so the reason I wrote it like this is because I'm giving myself some space. Now, the way this worked was, if you remember the pattern, the first term in the binomial, the x, starts here with the biggest exponent, and then each consecutive term, it goes down 1 in power. The last term has 0 x's. The second term, y, goes the other direction. It actually starts back here with the biggest exponent, and then 6, 5, 4, 3, 2, 1, and then the first term has no y's. And then I just put plus signs between all of these, and this is the expansion of x plus y to the 8th. If you want to prove it and actually multiply it out 8 times, that's fine. Go ahead, do it. You will get this. Let's try it again with something a tad bit more complicated. So now we're going to do x minus 5y to the 7th. So the first thing I need are the coefficients from row 7 of Pascal's triangle. So now I got to go back here and find out what row 7 was. It was 1, 7, 21, 35, 35, 21, 7, 1. So if I can remember 1, 7, 21, and 35, I'll be good. Let's see. 1, 7, 21, 35, 35, 21, 7, 1. I think I got that. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay. If it's a 7th row, it should have 8 terms. The first term in the binomial, which is x, starts here with the largest exponent. In each consecutive term, it goes down by 1. The last term will not have any x's. Now this is where we have to be careful. This is where the problem is just slightly different. The second term in the binomial is negative 5y. So it's going to start over here with the largest exponent. Notice I put it in parentheses. This is going to be negative 5y to the 6th, negative 5y to the 5th, negative 5y to the 4th, negative 5y to the 3rd, negative 5y squared, negative 5y to the 1st, and the first term will not have a negative 5y in it. And there are plus signs between all of these. The other part that makes this different is we're going to simplify each term. So the first term is 1x to the 7th. For the second term, remember that multiplication is commutative. So it doesn't matter the order that this is written in. I can multiply 7 times negative 5, which is negative 35. And then x to the 6th y. For this term, I'm going to multiply 21 times 25. Where did the 25 come from? Because I need to square this. Negative 5y squared is 25y squared. And 21 times 25 is 525. So it's going to be plus 525 x to the 5th y squared. All right, the next term, I'm going to multiply 35 times negative 5 cubed. Negative 5 cubed is negative 125, so 35 times negative 125 is negative 4375 x to the 4th y to the 3rd. The next term, I'm going to multiply 35 times negative 5 to the 4th. I should have put the parentheses there. When you raise a negative to an even power, it will become positive. So it's going to be positive 625. 625 times 35 is positive 21,875 x to the 3rd y to the 4th. The next term is going to be negative because I'm raising a negative to an odd power, and negative 5 raised to the 5th power is negative 3125, and negative 3125 times 21 is negative 65,625 x squared y to the 5th. The next term is going to be positive. Notice that it's alternating. Negative 5 to the 6th power is 15,625 times 7 is positive 109,375 xy to the 6th. And then the last number is going to be negative. And negative 5 to the 7th power is negative 78,125 y to the 7th. This is going to lead us to something called the binomial theorem. The binomial theorem says if you raise x plus y to the nth power, the first term is going to be a combination of the exponent 0. If you don't remember combinations, there was a formula for how combinations worked, but we're not even going to worry about that. We're going to do it in the graphing calculator. So if you want to do a combination 8, 0, what you would do on the graphing calculator is you would first type in 8, and then you would press the math button, and you would arrow over to PBR, and number 2 is NCR, and it'll pop up like this in the screen, and then you would press in 0 and then hit enter. What that combination is going to tell you is the coefficient of each term in the binomial expansion. The reason that's good is because if we ask you to expand something to the 35th row, you don't really want to find all the coefficients in row 35. Now here in example 2, although you probably wouldn't do the problem quite like this, I'm going to show you how the binomial theorem works. So notice that 4x plus 2y is being raised to the 5th power. So let's say you didn't know the coefficients and you wanted to find them. The first coefficient would be C50. The second coefficient would be C51. The next coefficient would be C52, and then C53, and then C54, C55. Look at how many terms we ended up with. We ended up with 6. Remember I said earlier that whatever the binomial expansion is 2, whatever the exponent is, you'll have one more term than that. So if you put this in the calculator, you would put in 5 NCR0, which will give you 1. And then you would put in 5 NCR1, which will give you 5. Then 5 NCR2 is 10. 5 NCR3 is also 10. 5 NCR4 is 1. And 5 NCR5 is, nope, there I said 5 and I didn't write that, and this is 1. So that's how you would find the coefficients. But we know the coefficients because the 5th row of Pascal's triangle is really easy to get to. So now we know that the coefficients are 1, 5, 10, 10, 5, 1. So now I'm going to go get rid of this, and we're going to expand the binomial. One, 5, 10, 10, 5, 1. So the first term in the binomial, 4x, starts with the biggest exponent, goes down 1 each time. Squared, and then 4x to the first, and the last term doesn't have 4x. And then the second term, 2y, starts at the end with the biggest exponent, and then goes down 1 from there. 4, 3, 2, 1, and then the first term doesn't have a 2y, and these are all plus signs. And then we go and we simplify each term. So the first one would be 4x to the 5th, so you have to raise 4 to the 5th, and you get 1024, x to the 5th. And then in the second term, you're going to multiply 5 times 4 to the 4th times 2. And then you're going to multiply, and then at the end you'll have x to the 4th y. So you get 2560, x to the 4th y, plus, in this one, you're going to multiply 10 times 4 to the 3rd times 2 squared, which is also 2560, x to the 3rd, y to the 2nd, plus this one, you're going to multiply 10 times 4 squared times 2 to the 3rd, which is 1280, x squared y to the third, plus this one you're going to multiply 5 times 4 times 2 to the fourth, which is going to be 320. And the last one you're going to do 2 to the fifth, which is 32, y to the fifth. So what's in green is the final answer. Now what if I just want to find one specific term in a binomial expansion? I don't want the whole thing. So for example, in example 3a, I want to find the fourth term in the expansion of 2x minus 3y to the 12th. Well, how am I going to find that? So I'm going to give you a very simplistic formula, I guess you could use for figuring out what the fourth term is going to be. So we know that each time you go to another term in the expansion, so like if this is raised to the 12th power, then the first term is going to be C12 0, the next term is going to be C12 1, the next term is C12 2, make this look nicer, C12 2, and then the fourth term is going to be C12 3. What I want you to notice is that the term I'm looking for, the fourth term, is one more than this. So for the expansion, you're going to do, we're going to call this n, where n is the power, and we're going to call this r, the term you're looking for. So the combination that you're going to do in your calculator is always going to be c comma n comma r minus 1. All right, so let's put that in our calculator and figure out what the coefficient of the fourth term in the 12th row is. It's 220. All right, now we have to figure out what the exponents on each of these terms is going to be. So I know it's going to be 220, and then I'm going to have some power of 2x, and I'm going to have some power of negative 3y. Well, here's where it gets nice. This is the term minus 1. The two terms, or the two exponents, need to add up to this exponent. So this has to be 9, because 9 plus 3 is 12. So I should have mentioned that back here when we did the binomial theorem. The exponents here always add up to the power that you're expanding to. So if you come back over here to problem B, the first exponent was 7, and this one was 6 plus 1, which is 7. 5 plus 2 is 7, 4 plus 3 is 7, 3 plus 4 is 7. If I go to this problem here, the exponent was 5, so 5, 4 plus 1 is 5, 3 plus 2 is 5. The exponents on the terms always add up to whatever power you're raising it to. So now I can finish this off by doing 2 to the 9th power, which is going to be 512. So this is going to be 512x to the 9th. And then I can raise negative 3 to the 3rd power, which is negative 27, and then it's y to the 3rd. And now I can multiply 220 times 512 times negative 27, and I get negative, I guess it's 3,041,280, x to the 9th, y to the 3rd. Let's try this again. Let's find the 13th term of the expansion of 2x plus 3 to the 15th power. All right, so I said that the coefficient of the 13th term, this is r, this is n, so cn r minus 1. So the coefficient is going to be 15 comma 12. The other thing we're going to do is we're going to do some power of 2x and some power of 3. What's the power of 3 going to be? It's going to be 12, because it's always this number. So if that's 12, then this one has to be 3, because the exponents have to add up to 15, which is the same as the exponent that you're raising the binomial to. So now we're going to plug this into our calculator and find out what 15 NCR12 is, which is 455. And then we're going to multiply that by 2x to the 3rd, which is 8x cubed, and then 3 to the 12th power, which is 531,441. And now we're going to multiply these three numbers together, which is going to be a huge number. Let's make sure I don't screw it up. 193,444,5240. 1,934,445,240. X cubed is going to be the 13th term in the expansion of 2x plus 3 to the 15th power. And that is the binomial theorem.